Alright, next we're up to what we call equilibrium. So if something's in equilibrium, it means all of the forces are all balanced and the things, well, one, it may not be moving, or secondly, if it is moving, then its velocity is not changing. So if the resultant force is zero, that's what we refer to as something being in equilibrium. And as it says here, it will have zero acceleration. So if it has zero acceleration, that means one of two things. If it's at rest, it stays at rest. And the other thing is, if it is moving, it continues at constant velocity. Alright, so let's have a look at an example. Here's example 21 that I've got here. Forces of 2, 4 and 5 Newton act on a particle in equilibrium. Sketch the triangle forces represent these three. Alright, so the resultant force is equal to zero. So that means that whatever we start off with, when we I'll do it. So if we sketch the triangle, so what it means is we've got these forces here like so, and the angles, it doesn't matter, but say that's 2, that's 4 and that's 5. Then this particle here that they're acting on doesn't move. So when we put them head to tail, if it's at equilibrium and if the result is zero, wherever we started from, we end up at that same spot. It's bad looking. I'm going to need to draw a bit bigger because I need to get my triangle going. Alright, but what we do know, as I said, is that when we put them all head to tail, that, we end up getting back at the same spot. So if that one's, say, the 2, that's the 5 and that's the 4, then that's what we would end up with. Alright, so find the angle between the 2 and the 4 Newton forces. So we're interested in this angle in here. Alright, so we're asked to sketch, and now we've got to find the angle between these two. Alright, so where are we? Sketch the triangle of forces represent the three forces. There we are, done that. And now find the angle between the 2 Newton and the 4 Newton force. There, I've made sure I've got that, the right one there. Alright. So we've got 1, 2, 3 sides that we know, one angle that we're looking for. So we're going to use, so this is part A. So for part B, we're going to use the cosine rule. Alright, and so it's this one squared. So it's always the opposite, these things. So 5 squared is equal to 2 squared plus 4 squared. Minus 2 times 2 times 4 times cos of theta. Alright, what do we got? We got 25, 4, 16, 16 cos theta. So I've got 25 minus 4 minus 16 equals negative 16 cos theta. And then when we go down a bit more, 25 minus 4 is 21, minus 16 is 5, I believe. So it'll be 5 over negative 16, because it's going to divide by 16 is cos of theta. And so cos of theta, when you stick that into your calculator, cos minus 1 of 5 on 16, negative 5 on 16, and that would be 108.2 degrees is what we get out. Now, what that means is that my triangle that I've drawn is not quite right, so this angle would be going over to here, and so what we would be after then, if the angle between them, normally we would express the angle between them as the smallest angle, and that's how my diagram looks. So let me draw a little part of the diagram. All right, so if the 4's here and that's 108, actually the 2 should be pointing that way. And so what we found is this angle in here, and normally when we're expressing, get rid of those dots. Yeah. And normally when we're expressing an angle between two vectors, we'd go for this smaller one here, call it alpha. And so all alpha would be is 180 minus this 108.2 degrees. So what's that, 71 point something, 71.8, isn't it? 0.8 degrees. Alright, that's because when I drew my diagram up, I drew it up here, not to scale. Actually, it should be more like that one that I've got there, shouldn't it? And then the 5 would go here. Alright. Alright. But, you know, you weren't asked to like draw it to scale, so you're just asked to draw a triangle. But I guess, yep, I could have probably done a better job at it, but anyway, not to worry. All right, as long as you recognise when you get down here through the maths, that inside angle there is bigger than 90, and normally we would express as an acute angle an angle less than 90. All right, I'm waffling. Let's get to the next thing. Right, there's this thing called Lami's theorem. So Lami's theorem, effectively what Lami's theorem does is means that we don't have to go and draw a triangle like this and then use things like the sine and the cosine rule. So Lami's theorem, and if you want to look it up and you want to know more about it, you get to this essentially by using the sine rule. So it saves us a little bit of mucking around. So we've got these things there in equilibrium, and so P and the angle P is the one, I guess it's opposite to where P joins. So it doesn't include P. Alright, so P over sine P is the same as Q over sine Q. It's the same as R on sine R. So, and even when you look at it, there's some very close similarities to the sine rule there. Alright, so Lami's theorem, we can use Lami's theorem. Left a lot of... Alright, so find P and Q in the system of forces shown. Alright, so first of all, if that's 100 and that's 120, that's 220. And 360 minus 220 is 140. So this angle in here is 140 degrees. So using Lami's theorem, P over sine 140 is equal to, well, the one we know is this 10 Newton, and that 10 Newton is related to the 100, so it's 10 over sine 100. So P equals 10 sine 140 over sine 100, and then you get your calculator out and you stick that in your calculator, which I need to do because I didn't write this one down. Alright, 6.53. So 6.53 Newton. Alright, the other thing we were wanting to find was Q, and so similar calculations. So Q over the opposite angle is 120, and again 10 over the sine 100, and so Q equals 10 sine 120 all over sine 100. And again, you get your calculator out, you do all of that in your calculator. Alright, so 10 times sine of 120 divided by the sine of 100, and we get 8.79 for this one. 8.79 Newton. So there you go, there's Lami's theorem. Alright, so saves us drawing diagrams, saves us figuring out angles and then using the sine rule. As I said, its derivation comes from the sine rule, and if you're interested in that, you can look it up. Alright, let's have a look at another example. So the angles between the three forces of magnitudes 10 Newton, P Newton and Q Newton are acting on a particle 100 and 120 respectively. Find P and Q given the system is in equilibrium. Alright, so I'm going to just use a different, well, let's have a look. Angles between 10, so 10 P and Q. So I'm going to put 10 Newton there. Get rid of those. 10 Newton there. P's up. And Q is this way. And the angles between 10P and Q are 100 and 120 respectively. So I'm going between 10 and P is 100. And between P and Q is 120. And I'm just going to leave that at that. So I said I was going to show you a different method to find P and Q given the system is in equilibrium. So we could work out this, and we could use Lami's theorem just like I did before, but I'll show you a different method. And the different method goes this way. If I split up these vectors, it's bad drawing, split up that one, and split up the other one into components like that. Alright, and so then what I can do is I can say, if you like, looking in the I and the J directions, and equilibrium of course means that the resultant force is equal to 0. So if I want to use I and J, what I can do, and I've drawn this, and I haven't mentioned this, but I've drawn this so that I'll make that a right angle triangle there. So if that's a right angle triangle, this bit there is 10, because that was 100 degrees, not 180 that looks like. And also that's a right angle there, and so that's 30 degrees. And this is a right angle triangle, this is a right angle triangle. Alright, and so the I direction is here and the J direction is this way. so for my I direction, in the I direction, that's horizontally, because I's put to the right, the one to the right, so this component here, which is next to, so it's cos, so that's 10 cos 10. Minus, because this one's pointing the opposite direction, and that's q, cos 30. I plus, then in the j direction, well, p's pointing up in the up, so it's just p, and it's pointing in that direction. So I purposely made my I and j's so that j pointed up there and then I was at 90 degrees. And then I've resolved each of these into perpendicular vectors. Alright, so p plus, not plus, because these next ones are in the negative direction, aren't they? This one here and this one here is pointing down. So it's minus how much? Well, we've got this component from the 10 Newton, which is 10 sine 10. And also in that direction, we've got this one here from the Q, which is Q sine 30. J, and that's equal to 0, or just squeezed it in. Alright, so now what I can do is just look at each of those components. So what I know is that 10 cos 10 minus q cos 30 has got to equal 0. So let's do a bit of rearranging. If I take the q over there, so I've got 10 cos 10 equaling q cos 30. And then divide by cos 30, so I've got 10 cos 30, cos 10 I should say, over cos 30 equals q. And then what we can do is we can then get our calculator out, and when you do that you find that q is 11.37 Newton. And then of course so that's the I direction. And in the j direction, we'll have p minus 10 sine 10 plus q, which we've just found out, 11.37 sine 30 equals 0. So p then would be equal to all of this stuff, which when you put that in your calculator comes out to 7.42 Newton. Alright, so there's another way of approaching some of those questions. So Lami's theorem, or you can put it in and work in terms of I and j, and then resolve our vectors. So when you do that, if you do the I and j, choose one of those vectors as being in the j direction or the I direction, but in this case, one that points in the j direction. That makes life easier when you do it like that. Alright, if there's anything you need a hand with, make sure you get help, and as always, have fun.